Welcome to this session about Python for HPC, which will be presented by Damien Lozano from ULB.
Hello, everybody. So welcome to this session of how to make an efficient use of Python on the cluster. So I'm going just to switch to the presenting computer. So this session is divided in two main sections. One first section in which we'll review a little bit some tools that we have for doing profiling of Python code. So some tools to get an insight on how much time is being used by different functions that you might have in a big Python code, and how to monitor also the memory usage by the memory by the different functions, or the memory usage during the whole runtime of your code. And then a second part, we will see a little bit how to make a more efficient use of the hardware internals. Basically, well, that will mean somehow having to, as you know, Python is an high-level language, dynamically typed, that provides a lot of flexibility, but at the cost of being less efficient especially for intensive numerical calculations. But then at some point it will involve making a more efficient use, involve compiling code. So there are already a lot of extensions, Python extension on the Python ecosystem that are basically wrappers to libraries, highly efficient C and Fortran libraries precompiled that you can make use through extensions like Numpy or Scipy. But we will see also a little bit how we could also, for a custom function we might have, how we can ourselves compile a function and call it from a pure Python code. And then at the end, I will just give an overview of 2 or 3 different options that we have for using multi-cores in a given computer from Python. So for the first part of the profiling tools, we will be making use of a kind of a toy problem. It's based on this ancient algorithm for finding all prime numbers up to a given limit. So here I introduce it quickly. Basically, the recipe of the algorithm is if I want to find all the prime numbers up to a given limit, up to 25, for instance, I must initially create a list of all the numbers up to that limit. And then in the first step of the recipe of the algorithm, I start with the first number, so 2 in this case, and then I jump. I make on this list displacement multiples of this number I'm standing. So 2, I jump. I do displacement through the list multiples of equal to 2. And I cross out all those numbers. So basically, I'm crossing out all the multiples of 2 on that step. And I do that up to the limit. Then on the following step, I move to the next number that has not been crossed out on the previous step. In this case, it would be 3. And I do the same exercise. I jump 3, I jump 3, I jump 3, and I cross out the numbers that has not been crossed out. And then, well, in the following step, the same thing. I move to the first number that has not been still crossed out, so 5, and I do displacement equal to the number I'm standing on, equal to 5, and I cross out what has not been crossed out still. At the end of my procedure, I will have crossed out all the non-prime numbers, and the remaining, so 2, 3, 5, 7, are the prime numbers that were present in my original list. So you can see that there's a trivial optimization of this algorithm that I don't really need to repeat this step up to n for a list of size n. It's enough if I for each time I jump to a given, I start a new step, I can start directly. I can jump directly to the squared of that n I'm standing, so to 9, and then do displacement from there. So you see here when we reach 5, I jump directly to start crossing 5 squares or 25, and I'm done. I can see that all the previous number before n squared has already been crossed out in the previous step because they were multiples of the lower numbers. So then how it would like a simple pure Python implementation of this algorithm. This is one possible option. So I have my function that will return me all the primes up to a given limit that I can call them from another parts of the code. And so on this function, it's creating initially a Boolean list. This Boolean list will represent my CF list, and it will be of the size of the limit. And then I will assign the value. So if a given index has it's equal to is false, it's because it has been crossed out. If a given index is true, it's because it's not crossed out. So I initialize. So for simplicity, it's easier to create the list, to think of the list as starting of 0 instead of 2. So we have 0, 1, and then all the numbers up to the limit. So for that reason, I create a list which will be size limit plus 1, and then I'm setting as false the 2 first elements, which are 0 and 1 that are crossed out from the beginning. And then so I have here the loop in the end loops, the end outer loops I will have to do from 2 up to the square root of my limit, as I mentioned in the previous slide. And then for a given n, I create another index that jumps directly to the n squared. And then here is where we do the actual crossout. Here is where we actually go through the list doing displacement equal to n from starting from n squared up to my limit. And then, well, so here after I did this, I went through all these loops. My CF list will be a list of booleans in where it will be only through the index that are representing a prime number. So I'm returning here the function is returning the reduced list of the elements that ended up being true. And so that it's some kind of simple way of a very pure Python implementation of implementing this algorithm. So if I want to time something that it's not running for hours, but for seconds or minutes, if I want to have a quick overview of how long it's going to run something, you're probably already familiar with the time command from the shell in this case. So if in the bash shell you put time before a given command that you're going to run, you execute that, and then it will print on screen how long it took to run the command you introduced after time. In this case, this little script I'm running is the same thing as before, but I'm already hard coding here 30 million, and I'm not I'm avoiding the print because I will have a flood of output on the screen if I print all the primes up to 30 million. But so we can see that running that code, this is just in a 2 years old laptop, i7, running that simple code up to get all the primes up to 30 million. It takes about 10 seconds. And then more Python specific, if you are working on tuning some specific function in a Python code, you can make use of the timeit module that you have available, that it will give you an average of several runs. So you do a loop you do 3 loops, and you get on each of those 3 loops, you make 3 runs and you get the best of each loop, and then it will print you the average of all those loops. So here, but yeah, you have to call it this way. You have to, like, if you have your cf01.py, you have to give it to the Python interpreter. You have to import it this way if you have your code named like that, and then you can evaluate a function from interactively. So that you can use also maybe as quick tests if you are working on a given function. But yeah, I said that we are going to see some profiling tools. So the first one I'm presenting here is the one called cProfile. This is built in on Python. It's part of the standard library. So in any Python installation, it's already available there. And so when you run your code by calling interactively this way by loading this module, it will hook into the Python virtual machine, and it will monitor how much time is being used by every function that the Python virtual machine sees being executed. So if I run, this will introduce a little bit overhead from the runtime that you have if you run it without calling this profiling tool, but not that much. And so after you run it, the same code as we had before. So CF01 get asking the primes up to 30 million. We see it will print for something like this on the screen, and it will give you the main column maybe is the number of calls. In this case, we're just calling only once each function. We have a single function on my code. But in a more complex code, yeah, this can be relevant to see how much are you calling each different functions. But then it will give you also the total time. So from the total runtime of your code, it will give you a summary of how much time of that total time was used by each different function that the Python virtual machine executed. So we can see here that as we can expect, the only function that we have in the simple code is the one consuming most of the time. We see some, so this is like 90 and 10%, so it's not negligible that being consumed by a list comprehension. This is the return of the very end of the primes up to, so it's the returning the value of the reduced CF list, so the value of true booleans. And so for a simple code as this information on the screen can be enough, but for big codes you can dump the information from this cProfile tool instead of to the screen to a binary file by giving this argument -o and the output file where you want to dump that, and then you have the tool called snakevis that will be able to parse and give you a nice visual representation of that output. So snakevis is, well, you can see if you're in Linux, if it's available. It's available in most Linux distribution in the repositories. Otherwise, you can pip install it. And so I will show more or less what kind of, if we run let me so if we run the command as with invoking cProfile with the -o to profile.stats, I will get that, and then if in this case I won't see the input on this machine because I'm running this in my work machine that connected via SSH. So for you to see, it will actually create a small web server, and it will pop up, if you're running this locally on your machine, it will pop up a web browser, and you will see the output that looks, I made a, so you will see the output this way. I'm zooming. As I said, in a local web browser in your machine, and you can actually click and interact a little bit with the information. So for that reason, is that it does this. It shows it via this local web browser, so to have some interaction. So below you will have the table of the values that you see on the screen. Here, this has been run in a different machine from the one you see the results of the presentation. So in this machine, the total runtime is not 10 seconds, but 7 seconds. But so basically, you see the first rectangle on top is the full length of that is represented the full length execution of your code. So the 7 seconds, and then below you see functions. A hierarchy of functions. So, so this is the main Python virtual machine that then it's executing the CF01 code that we ask to execute, and then this code has the prime subto function, and inside this prime subto function, we have the list comprehension and the function itself. But if I have a more complex relation of different functions calling others, you will see the hierarchy of, so the bottom, the function on the bottom depends on a function is being called by a function before, but then you can see how much time on a given part, on a given place of this hierarchy, you can see how much time is being consumed from the total time, so relative to the total time. So here, it's another way of seeing the table that we were seeing on the screen. Sorry. So it's another way of seeing the relations of this function and the total time. If you have a big code, it can be really useful to spot the results like that. So let's say that once that you identified a given part of your code that it's the most I see that I got that. Sorry, a pop-up of I'm not using. Sorry, I got confused as I'm checking my live presentation on a different machine next to me, and I got a pop-up there that I thought it was blocking the presentation, but no, it was a pop-up in the machine next to me. So as I was saying, if after I determine some given functions that are the ones that are consuming most of the time of my code, if I want to get a more detailed view of inside that function, we have an interesting tool called the line profiler, which will actually, well, it will give me a detailed view of how much time is being spent on each line of a given function. So this one is not included in the Python standard library, but it's you can easily pip install or check also if it's not available in the repos if you're using a Unix. and then the way to use it is you have to modify your code, but it's very minimal. You have to introduce a decorator, so an add profile decorator on top of the function that you want to analyze with the line profiler. And then, so this is the initial code that we were calling cf01.py, and so we just add the add profile decorator there, and then we run the code. I rename it like that. I will then tell you where you can find this in the cluster. After you have your code named like that, where you added the add profile decorator on the function that you want to get the detailed view, you run it with the current prof tool, and sorry, it's the machine next to me with pop-ups. You run it the code with the decorator with the current prof tool, which is a script provided with the line profile Python extension, and then it will output information on the screen like this. So for the given function that you ask to be profiled with the line profiler, you will get actually, well, you see here, you get the detail, the lines of the function that you're profiling, and it's also giving a similar information as we were getting before, but before it was for the full run of the code and only at the function level. But here we see inside a function a similar information as before, how much time is being consumed on the total execution of this function, how much time is being consumed by each different line. And so we can see that here, yeah, not surprisingly, for the 100% of time spent in this function, more than 90% is being spent in these three lines, which is the most inner loop where I'm going to loop the most. Here I see that I have a gigantic amount of hits of these three lines. So it's well, the lines, the most inner loop where I'm crossing out all the primes several times. And so, yeah, just as I mentioned, take into account that the percentage that you see here is just relative to the time consumed only for the execution of this function. So 90% of the time was spent here, but that means of this function. It's not of the total time of execution of your code. Take into account that running this profiling tool to have this very detailed view, it will introduce a real big overhead. It will be about 10 times. It will take about, well, for a given function that you ask to profile it will be 10 times. It will take 10 times more time to be executed to get this information. So when you're doing this kind of tests, you have to always reduce your problems. And then a part of the line profiler, we have a kind of analog for memory usage. It's called memory profiler. And it's capable also of giving a detailed view of actually of the memory usage by each line of the each line of code inside a function. I have to also introduce the add profile decorator to analyze it with this approach, and it will give me, so after the code run, it will output this information, giving me how much memory or increment I had after executing each line, and then, well, the total memory usage. And, well, the important thing is mainly more the increment. So you can see that here after going through the line of the creation of the line of the creation of the CIF is the only thing that actually I'm allocating memory, and then I'm just crossing out that list. I see that the creation of that list of 30 million booleans is it gives me an increment of 228 megabytes. Then it's say constant. There's no memory increment, and yeah, I'm just crossing out that single element that I'm working on that single element. But take into account that this it will be even slower than for the way it works. It will be even slower than the line profiler, so it can be up to 50, 100 times slower than running this profiler attached to your code than the line profiler. So we might wonder why we have this kind of huge amount of memory allocated for saving this when we create this object, this Python list of 30 million elements. And so we can do a little bit of math, and we have to take into account that by default, when you create when you create a Python list, by default, each element of the list will take at least 8 bytes. Then, depending on what I'm going to store there, it can even take more space on memory. But by default, the minimum amount it will be 8 bytes. So for a boolean, it will stay like that, or small integers. And in this case, we are creating a list with 30 million elements, being 8 bytes taken by each element. That times 30 million, and we divide to go to kilobyte to megabyte, and we end with the value of the 228 megabytes. So a list, an array in memory of 30 million elements of 8 bytes, it takes that amount of memory. And so as here I already mentioned that doing the memory profiler is really, it will take a lot of time to go through your code with that tool attached. And actually we can, as we are going to see now, we can actually even miss information even if we get a lot of details. And the same memory profiler package is, it provides another tool. So when you install this Python extension, you will get also an mprof binary. That it's really useful to see how much to monitor the memory usage of your code as a function of the runtime. And then I think it has a really very small impact on the runtime of your code. And well, this is how you would use it in 2 steps. So you will run your code. It will dump a given file. That then the same tool, calling it again with mprof plot, it will read the latest. It will have a date timestamp, and by default it will take the latest. And it will, with matplotlib, it will give you a nice plot like this for my CF01 code. And also we don't need to run it with this. We don't need to modify the code at all. So here I'm running it with the very first version I presented. So we don't need decorators. So you have a code, you just run it with these options. And then you run mprof plot, and as you can see, from 10 seconds it went to 11 seconds, so the overhead is not that much from 10 seconds running it raw on its own. And then yeah, you see here, so we have the runtime and the memory use during as a function of the runtime. So we see here an increment of 200 something megabyte that we saw. They are due to the creation of the CF list, but then we see a spike of the double of that amount. That spike is gone, and then we see that we stay constant using memory 200 the 200 something megabyte that we allocated for the list. So here we are working on crossing out that list. We are not allocating more things to memory. Here we have then at the end a small increase, and this we can see that this match the size of the array. So this is the part of the return. So the list comprehension doing the return of the true values of my array. So it's actually allocating in memory the small array with the reduced amount, only the primes that I'm going to return, and then well the code is done. So as you can see, this tool can easily give me a nice overview of memory usage as a function of time, and then it has even, as I said, I can run it plain on a code without modifying it at all. But if I want to have some more, if I want to visualize some more details about it, we can add the profile decorator, and then we can use this method, the timestamp method, and it will, when I run it with the mprof, then this will only make sense to run it this way by calling the Python interpreter and by via mprof. And so we add a timestamp, create CF list, and everything that is indented in this width will be identified. It will be indicated in the plot, as we will see. And then we add another timestamp, and here we mark all the part which is cross out the sieve. And so when I run again, that code that I just showed, with those two timestamps, then automatically we just run it like that, mprof plot, and you will get a matplotlib plot in which you have the indicated with the brackets and a color. So the green brackets is a part of the interval, the time interval where of everything that I put inside that width statement of that timestamp. So this is the part doing the create CF list. So we see that the spike happens during the creation of the CF list. Then we have the section of cross out the CF. So with this blue cyan brackets, so we see that the memory stays stable during all the crossing out, as we are not allocating anything else in memory. Then we have the return, as I say, and then we exit fully the function. And actually, when we exit fully the function, we dropped the CF list, and we keep in memory only the value returned. So as you can see, this so adding these timestamps if I have a bigger code and I want to get to organize a little bit the output that I see, it's a nice way to add more information to my plot very easily. And then so we can wonder why we have this spike here. If we play a little bit with this tool and the code that we had at the beginning, we had so far we have the creation of the CF list declared this way, and we can actually, experimenting with the mprof tool, we can actually see that for the Python interpreter or the Python VM, when it executes the line, it will execute it equivalently as if we were doing all these steps. So actually creating a small list of only 2 elements, false, and then a small list, a big list of 30 million, almost 30 million elements, and then doing the addition of these 2. And so here we allocated a list of 30 million elements, so 228 megabytes. Here in this step, we are allocated a new list, the one that we'll stay using afterwards as a concatenation of the other 2. But so at this moment, we have 2 lists of 30 million elements allocated in memory. So and this second step is producing that big spike, the double of the 228, and then it's deleting these two temporary partial, the CF1 and CF2, and we stay only with this one. And so we have the spike precisely in the moment of allocating this second. But at the end of the execution of all this line, we stay just with this single one in memory. And so if we can also experiment it with the mprov, then we can change this this line that we had originally by something like this. We initialize just a single, so we create the CF, the big list of Boolean CF, just equal to the full size, so the 30 million plus 1. Remember, yeah, that we will have the 0 and 1. And then we say, okay, 0 and 1 are false. We cross them out, those indexes, the value for those indexes. At the end, we end of the main result. So the CF list at the end of these 3 steps is the same as all this, creating it this way that is doing all this. But if we then run the mprov tool for that, for changing the creation of the CF list of that way, just creating a single and crossing out 0 and 1, we see that we lose in the create CF list part of the code, we don't have the spike anymore. So we have only the jump of the 228 memory, which is, well, the allocation of that, of the list itself. Then we stay constant, and then the creation of the return list. So, well, yeah, as I say, this tool is actually smart. Using it smartly, it works both as a memory profiling tool and it can somehow a CPU usage tool, because here with the timestamps we can mark part of the codes, and then we will have here we have the total runtime of the code, so I can also see how long it takes it's taking in a given part that I timestamped. But yeah, for not so complex codes, for doing CPU profiling that way. So here we will do a small pause. I will take a look if there are questions. And here I won't ask you to go through this right now. It's something that you can keep for taking a look afterwards with calm. So in this folder, from any of the SESI cluster, so you can copy this folder to your home, and then yeah, when you copy it to your home, you can check in the exercises folder the README file. It will, well, give you the steps of how to create, load the corresponding modules and create a virtual M and pip install line profiler and memory profiler inside a virtual M. So you can take that as an exercise also to see how to work with loading modules and creating a virtual M and staying isolated there. And you can, it's a nice way to get used to work also in the cluster. You can have several virtual M's with different things installed on those, with different versions of the modules. Probably you saw already that we have, well, different versions of Python 3. We have Python 3.6, Python 3.7. So the information given in the README of how to create a virtual M, it can be useful also to get used to. So, but I'm doing a small pause. Yeah, we start in 5 minutes, but you can. So I will show just that I checked before, but. What's insane is so you can login like Dragon 2 and yeah. Yeah, you see here the folder I propose to copy, and inside there you have the exercises. So I already copied as I proposed there on the slide. So on my home I can just see it there, and then I think I will copy this to be sure. I open the file that you are going to see. So here, as I said, here I have the proposition of in Dragon 2, which 3 modules you can load, or in Lemaitre 3, which 4 modules to have a Python environment where you will have NumPy, SciPy, Pandas. You will have Numba that we will see later, Matplotlib, and in Lemaitre 3 you have also IPython available as a module to load, and then but here are the steps actually. So when you are loading modules in a cluster, and then you are creating a virtual env, it's important that you initialize your virtual env adding the -- system side packages option. So that way you will actually be using the inside your virtual env, you will using all the things available outside or from the modules that you loaded. And then when you do pip install of something that have a Matplotlib or a NumPy dependency, you are using it from the modules that we provide, and you are not getting them from pip also pulled. Remember, all the things that we provide installed will run way more efficient in the clusters of the hardware than the pre-packaged binaries that you get with pip install. So then, after you initialize a virtual env, you source to activate it, and then you pip install inside there. Then remember just that if you log out to the cluster and then you log in, you will have to repeat the module loads and the activate of your virtual env. And also, as I said, the examples. So in exercises, you have exercises that you can consider as like homework to look if you want to explore the thing. But then in examples profiling, you will see the exact same files that I was mentioning on the presentation. So if you want to test, you can run the same commands. Okay, so I see from the question Damien already answered. I have no experience with PowerShell, so I would have to Google also. But yeah, you can experiment on the clusters. Regarding the question about the time on PowerShell, and then yeah, also it was answered by Damien, but in Python allows that kind of syntax for instantiating a list. You can just put into brackets a given element, multiply it by n, and then you get automatically, you are creating a list of n times the same thing. And you can actually add list between them, as we are doing in the first part, adding that list of 2 elements plus the other of 30 million. And so, yeah, well, in the everything that you see with this like light blue color is an hyperlink. So probably, yeah, if you're seeing opening the PDF that it's in the Indico website, you can click on that, and you will land in a website giving an explanation of what it's implemented in that in the exercise. It's a Python implementation. It's a pure Python implementation of the of solving the 2D diffusion equation. In the Python ecosystem, you have the main how to say, well, one of the main advantages of Python is actually the huge amount of things already done that you have in many different extensions for very specific tasks or very general. And of course, well, there's a lot on the numerical computation side. So we have the Numpy library. Is I guess you all must be using it for something, but it's the main library for anything related with the matrix vector operations. And it's mainly a wrapper of the C and Fortran, BLAS, LAPACK libraries developed since like 30 years. So, and those are super optimized C or Fortran code. And the thing is that from within Python, we can interact with that in a kind of very friendly approach. So you can consider this extension, particularly like yeah, as something giving me a friendly view on this very efficient low-level libraries. But we can still use it in a Python-like way or in a MATLAB-like way. And so here is a small example of how I create a matrix vector and do and evaluate in C the dot product of the matrix and this vector. And it's also also there are many other libraries built on top of NumPy. So the main thing, yeah, it provides me a new kind of array data type, a part of the array objects on Python that are lists and tuples. Here we have a new kind of array that actually we can have defined that it will have a mandatory, a well-defined data type for the elements of this array, and it will be allocated in a contiguous region of memory. So then when we do operation on these arrays, it's like an allocating a big C array, you profit of them for operating through these arrays. You profit that you are assured that they've been allocated in a continuous section of memory. And so on. So if what would happen, for instance, if we replace so my initial code instead of creating a list, a Python list with the booleans, we create a Numpy arrays of booleans. So here we are with a new approach that we saw after the memory profiling exercise. We create initially a single array of size limit +1 equal to all to 1, so all true. But here we are defining a data type for this array. They will be a NumPy Boolean kind of data, kind of type, and then we cross out 0 and 1, and then we do. Here is exactly the same loop in which do all the crossing out, and then we return the result. So the only thing we did was, instead of creating a Python list, we create a NumPy array, and if just like that, then for a NumPy array, data type Boolean, it needs only 1 byte to be allocated to be saved in memory. It needs to allocate just 1 byte in memory for represented a true-false value, which is more than enough. And so we see then that if we run the same code, but using for the C list a NumPy array, instead of allocating the jump that before was 228 something, now it's just about 20 something. And so we can see that so knowing that in a NumPy array, each Boolean has a size of only a single byte, we can see now that allocating those 30 millions of Booleans is taking just 28 megabytes instead of 228. And so we see that now that all the memory use. So well, it's not anymore a big jump. It's comparable with the Python list. It's less than the Python list being on the return. We could optimize that way. That also, but so we have just a 30 megabytes jump. Then we say constant during the crossout, and here we have still a Python list being returned. But so here you can see actually one of the benefits of using array objects, but which have a very well-defined data type instead of, well, yeah, Python is pure Python is very flexible, but that comes at a cost. And as I say, then operating, well, here actually we are not seeing any gain operating on this Boolean, but on this NumPy array, doing the crossout on the NumPy array or doing the crossout on the Python list is taking the same time, about 10 seconds. And yes, we will see that because we are not profiting at maximum of what NumPy can offer. As I said, we have many different methods to operate on this new kind of objects that the NumPy extensions provide, and they have very powerful methods actually for looping for doing matrix vector operations, which at some point means looping through objects in memory and then looping over an array itself. You have the functions that are called slide indexing. As I said, you can click that in your PDF and go to the documentation of that. But so we can rewrite all our internal inner loop instead of doing a Python for loop. So we still have a Python for loop for the outer loop of 2 up to the square root of the limit, but then the crossing out, we do it with the slide indexing syntax that allows us to jump and move through, to do an internal loop of an array, starting from the square root of n up to, in steps of n up to the end. And then if we create a NumPy array and then we move through this array with the methods that NumPy itself provides, so the slide indexes functionality, and then we return actually also, yeah, we just return, we don't do the Python list comprehension, we use another method also to return all the false value of that. We have a massive gain in our code. We go from 10 seconds to half a second, so like a 20x gain in time. And somehow this code still looks, well, it's still Python code, but just using a very powerful and highly optimized extension calling, so an extension calling highly optimized library. So the main thing is that, remember, if you are using NumPy, do not use, for working on those elements that you create with NumPy as the CF list, do not use for loops, use the proper methods that the NumPy, that the NumPy library provides to loop through them. So then you really profit of the fact that you are having this continuous, these well-defined arrays allocated in continuous memory. And so we can have, we can have, if we run now this NumPy code with the line profiler tool, we can have a view of where I'm doing the massive gain. So I remember this line profiler is attached to the Python VM and is telling me from the Python interpreter how much it's how many times it's hitting a given function, a given line of the code. So the Python interpreter itself, and we can see that before, if you remember here, well, in the most inner loop, we had also about 19% of the usage. So that's normal. We cannot avoid that. But you see that Python itself is just executing this line only 700 times. The one doing the most time-consuming part, so it's 90% of the time. The one doing the most time-consuming part by Python itself is being hit only 700 times. Before we have like 70 million. I think here, yeah. So here we have details on that. So this is the result I was showing compared to the result before. So the trick actually is that before it was a pure Python implementation, so the Python VM was executing everything, and now here it's only hitting. You can actually see that here it's only entering for each new I, it's hitting this, and then the full crossout. So these three lines are being done by moving through the indexes of this array with the internal NumPy slice indexing method. So it's actually C code running, doing all the crossout, and that's the reason to have the massive gain. Actually, you can look for options, an optimal option of based pure on C or Fortran that then you compile for solving this issue. And you will see that running it on the same computer, you will be on the same amount of time, if not even better. Because remember, yeah, this thing is doing on the back end is already a very optimized. It's using methods based on very already optimized C code. So that's, yeah, you can see what that was to a little bit to close the profiling part and to present and to give you kind of idea what it's behind of stuff like NumPy, SciPy, Pandas, what's behind all this Python extension that, yeah, are well known in the for scientific computing. Well, remember that always that we attach a tool to do profiling, we will have a huge overhead. An overhead, it can be huge or not, as we saw that the mprof tool is not that much and is really dynamics and really useful. But yeah, some others like the line profiler, it does introduce a really big overhead. So then, yeah, when you're going to debug or focus on a part of your code to optimize, you remember to run it with some smaller example that still makes sense to run it with. And then, okay, and here actually I didn't merge this. So here is another possible tool for the C profile tool. So instead of snakevis, you have this other tool, kcachegrind. The thing is that this one has a lot more dependencies. So it's part of the KDE ecosystem. So you have Qt. It's a huge package, way more powerful than snakevis. But snakevis is just, you can just pip install and then as it uses the browser as a backend, then it runs everywhere. But then, you can explore this also if you want. It's another tool that will, give you the same features and more that you had with with the snakevis to visualize the output with C profile of the time consumed by the different functions on a full Python code. So the NumPy library, well, it's part of a big ecosystem developed around scientific or numerical computation or data treatment. And as I say, there are other tools built on top of that, like pandas or scikit-image and scikit-learn. And yeah, well, you can explore as I said that before at some point, that the advantage of Python is that you have a huge ecosystem of extensions, very powerful and focused on many different problems, and so before, yeah. When you're dealing with a given so everything that is numerical integration or PDEs or resolution or everything related with linear algebra, all the basic parts that you will need to deal with in any kind of problem solving, the main parts are already implemented in some of those libraries, and so then you have to rely on those and focus on other parts of your code. Then, so now we already transition a bit to the second part, seeing about NumPy, and we are going to see actually how we can a little bit how these kind of libraries are built, how can we, for a given function, that custom function that we have on our code, how we can transform that if that started as a pure Python implementation or semi-Python, semi-NumPy, how we can get a part of a given function and transform it in a compiled code and then call it from pure Python code. And so that we have two main options to produce compiled code that we can call from Python. We can actually, well, we have what it's called just-in-time compilers, that actually that one, as the name says, they will just grab a Python code and it will compile it live on real time. And then it will run the code after. So when I execute it, it will do a fast compilation and run it at the same time. Well, the two main projects on this area are PyPy and Numba. PyPy, the main drawback of PyPy on the area that we are interested is that it's not compatible with NumPy or SciPy or whatever. So if you have in a code you have you are calling NumPy and you are making use of NumPy arrays, PyPy won't be able, it will crash, it won't be able to do anything at all. But for very, very pure Python code, it can compile it and run it. And then Numba is a very huge project. It got a lot of traction from Continuum Analytics. So they are the developers of the Anaconda environment for installing Python and R and extra stuff. I guess you might all be familiar with Anaconda. Remember, still that we have things, a lot of modules provided with the module tool in the cluster that in most of the time is even more optimized than the general binaries provided by Anaconda. But so Numba is it's a project, well, with a lot of active development, and it's going it's getting a lot of, well, it's been improved a lot, so it's something to look at. And then you have what are called ahead of time compilers. So that's basically a more traditionally compiler. So you have a piece of code, you compile it, you get a binary, and then you run that binary that you compiled at some point. And so you will. Cython is well, the most universal, but the most widespread project for compiling Python-like code and then call it from Python. Many of the different extensions that you might be using are developed on Cython. Even Numpy has some Cython code. And then there's Python. It's an interesting project. It's been active developed but just mainly by a single person. So it's been actively developed in the sense that it's not dead, but it doesn't have the the community around it is not huge, but it's some kind of nice tool to experiment. It will automatically convert Python to C++ and then compile it, but it will actually dump you the C++ code, so you can use it also to to do some kind of like language transformation, and then you can analyze that code. Maybe and you can grab that C++ code and keep working on that. And it's compatible with NumPy. Well, NumPy, I don't know if I said it, but it's also compatible with NumPy. So how these just-in-time compilers work like? So PyPy, here we will try to. So PyPy, as I said, you can just, you have a Python code, like the very original one, the pure Python implementation of my sieve, sieve01.py, and I can just run it with PyPy instead of with the Python interpreter. It will do some fast compilation and then run it. And then we have Numba, that in this case we need to do a modification, but it's minimal, at least for the very first approach it's very minimal. We just have to import Numba, and then we add the @JIT for just-in-time decorator on top of a function that I want to be pre-compiled. And then we can just run the code with the normal Python interpreter. If I have Numba installed, I'm importing Numba, so I must have Numba installed in my Python environment. So we will take a look how this thing would work. Notice that in the README file, Numba, we have it available in the Dragon 2 and Lemaitre 3. I didn't check a lot of inner queues, so you just focus on I didn't dig inner queues, so just focus on Dragon 2 or Lemaitre 3. The one maybe big drawback of Numba is that it's a bit hard to install, but yeah, we have it already available because it uses not GCC, it uses the LLVM compilers for doing the just-in-time compilation. So here, so before, if we compiling, no, sorry, profiling, I will look just for the sieve01. So you see, this is the very first code we were working with before, and here we should have PyPy3. So here I will just do the lazy time thing on the terminal just to show. If we run that sieve01.py here in Dragon 2, I think we get like the 10 seconds that we were getting on the, a little bit less than I was getting in my old laptop. And then if I run the same code, just with the PyPy, Well, you see, it will pre-compile it and run it, that binary that builds in memory, and you see that you get already a gain of 7x without doing nothing at all. But as I said, the PyPy needs pure Python code. If you are importing NumPy or creating a NumPy array, it will get lost. It won't be able to do nothing at all. And we already saw, that a NumPy version of that code, it's even way more efficient. Than we can actually try on the same machine for 604. So this is the pure NumPy, pure NumPy version, and yes, I don't have any module load. So actually, it was using the no, we'll get it first. So okay, it was fast. We see also from the 7 seconds on the same machine of the pure Python one, in the same machine, the pure the one using NumPy goes to 0.4 seconds. This is, remember, this is just some very lazy thing, very quick, and in this machine we are several login right now. So in case we have orders of magnitude of difference, then it's useful to see things with time, but don't use just time for real during real debugging and optimization of a code. But it's useful just for this use case of when you have things that are order of magnitude different. So for doing this thing, also it's nice, if you can, in your own environment, your own workstation, you can have these tools installed, because then you know that you can control the things that are running. You can be on the same, you can reproduce the same setup in which you are going to time and test things. So what? I show NumPy, sorry, PyPy, that just running the same pure Python version of the sieve problem. It would run in 7 times faster than running with the Python interpreter. But then, so here we have it's just the pure Python implementation with the Python list, and we will run it with Numba. So we as I said, we just have to do import to do this import on top, and then add the decorator on a function that we want to pre-compile before running it. Here we have just a single function, and then we need to have Numba in my environment to run it, and then if we run that. So it's also about 1 point something seconds compared to the 7 seconds if we run it. So I will show here that if we command the import and we comment the argit, and we run the same thing, it will go back to the 7, 8 or. So you see that, yeah, Numba, it's quite nice. And as I said, it has a lot of well, huge active development, a lot of backing from continuous analytics, and it's also in the latest version. It's also even to dump, not just precompile and run. It's also able to generate to precompile for running. So here I just uncomment it and run again. It's also able to precompile and run on GPU, so to generate live GPU code. I didn't explore this area, but it's something that they are actively working on now, and so it's something that you can take a look also. But yeah, it's as a just-in-time compiler for numerical compatible with all the extension used for typical extension used for numerical computation. Numba is like the way to go. And you can have again with a very little effort. So sometimes, depending on you might be happy with that if you I don't know, if you're not going to run that a lot, or or it's simply enough what you can gain a bit with this, instead of, as we will see then, if you want to go deeper with the ahead of time compilers, so to get parts of your code pre-compiled to a given binary, and then call always that binary to generate that, or you have to write or C or Fortran or C++ code or Cython. So these are things to look at, and the community around Numba is really active and big. So, and then in the here we are going to an overview of how porting a code to Cython would work. So Cython, actually, the thing is that to get started, it might be for simple porting. It's it can be easy to get started, but to really master, you need to really master and use it in its full power. You are actually learning a new kind of a new programming language, which is something in between C and Python. But anyway, you can start doing here. I'm showing how I would with the sieve sieve problem that we've been looking at so far, how the minimal thing that I could do to transform that function to a Cython code is just defining a data type for the variables that I'm going to work with in this function. So and then so this is a different file. It's .pyx, the extension that you have to read to Cython code. So you will pre-compile it. You get a compiled Python extension, and then you can, as any other Python extension, you can import it in a Python code and call it. So if you create this this Cython code for the primes up to function, in which we define as an integer the value, the argument, the value that we are passing to the function, and then ni and the primes that we are going to return. After compiling it, you can, I think in the next slide I show how that's done actually. So this code snippet I'm showing, I'm showing here. If you call it ciflib.pyx, you have to create a setup.py file it's some kind of makefile equivalent in Python that will take care of loading all the dependencies in order to compile this code. So the Cython dependencies and some others. So you create a setup.py file next to the ciflib.pyx, which is the code snippet I showed before. And then you, on that directory, you build a local, you do like a local installation of that compiled Python extension with this command. And then you just run the cif01.py, which in this case, it's being reduced as to importing from ciflib the function prime sub2. And then you can see that, yeah, you would get, well, in that case, so let's try what we would get here. We were going from 10 seconds to 2, but yeah, I was just doing almost nothing. So here we have the code snippet I showed, in which we are just defining the data types of the integers we are going to work with. And then yeah, we could try Python. Actually, I will. Sorry. We have already here the compiled extension that it will create. So you see, well, now it reappeared, it created that. And then, yeah, from it created the, so the compiled Python extension with the corresponding interface to be called to be imported from a pure Python code. And so yeah, I import my function from there, and then I can just ask. Yeah, okay, so here we need 0.8 from, I don't remember, 7-8 seconds that we were here. So that's, yeah, just to give you an idea of how, yeah, what, yeah, Cythonizing Python code would be. So this is the most minimal thing that we are doing here, but Cython is a language, a programming language on itself. So it's not just defining variables that you will do. If you're going deep into it. But anyway, if at some point you have a big project or a big code and that you are interested in start optimizing it, or you want to provide it as a distributed as a library to be installed and used somewhere else. Cython is one of the most widespread approaches to used to create compiled Python code. The community is huge. Like, I don't know, if you are stuck and you're having issues, you drop a question in Stack Overflow, you will have feedback for sure. So if you're interested in getting into it, it's a very mature and well-established project to get into it. If you're already familiar with programming in C, you shouldn't have big issues into coding in Cython. And then, here, I just mentioned at the beginning of this part, I mentioned about Python, which is going, it's doing also, it's generated also a local pre-compiled extension, a binary of a compiled extension, and it provides me the interface to recall from a Python code to import that library and to import that extension and run the methods of it. But the thing is that, as I mentioned, it's been actively developing in the sense that the project is in GitHub. It has commits every month, but the community is not huge, so there are several issues, and actually right now the latest version is having issues depending on the system libraries that you have for BLAS or OpenBLAS. And then, as the community is not huge, until they fix that, it will take time. So it's more, something to experiment with rather than to use it or decide to use it for a production thing. It's based. The idea is a mixture of just in time and Cython. Well, not really Cython, because it's not. This is not a programming language. So you get actually in a Python code, you put some kind of pragma, some annotations on top of a function that you want to generate a compiled version of it. So you are not going to precompile, but you generate a compiled version, a compiled extension that you can import. And in this kind of pragma-like, pragma in the sense of OpenMP, you will define the data types of the actually of only the input. You define the data type of only the inputs to the function that you are going to precompile, and then it will, the Python tool, it will do some analysis, and it's like a compilator at the end. So it will do some analysis and infer data type just from the rest of the thing from the initial information that you gave, and then generate. It will generate C++ code and compile it and generate on the same folder a compiled Python extension module that you can import. And the thing, you don't have to go through the ctap.py of CPython, but as I said, the project is, it's more something to experiment with rather than to use it for real things, for real production things. But it's there. You can have a look. But as I said, the very latest version, it will crash on the clusters, so we have to wait that the one that you can pip install. So we have to wait until they fix it. They have some issues open on the GitHub regarding that, and then so getting into the idea of, so far we see how to get a more optimized code. So basically how to compile code to then run or compile it on real time and run it, the Python code as a just-in-time compiler too, or already getting some piece of code and compiling it and getting a binary build, and then, well, having the interface to call this from a Python code, as we saw with Cython or Python. But we didn't see how to use multi-cores. So if I have, in the clusters, and even nowadays in any computer, there are several cores available. You saw probably some of you followed the OpenMP formation, and in which you had an introduction of how to develop code in which you can make use of to distribute workflow through different tasks, and sorry, I got the okay. But so Cython and Python, they provide the possibility to produce OpenMP code. So you can, inside a Cython code, you have well, special operators to get a loop to be well, if it matches with distributing the workloads through several cores, you can make use of these operators for creating a parallel part of your code. And then you have to add the -f OpenMP flag, and you can generate then a compiled Python extension that will use, when you call it from your Python code, you can in the backend use several cores. So actually, well, Numpy is already doing that by default for many of the functions that it has for linear algebra. Well, many other of the different scientific Python extension dedicated to scientific computing. But yeah, then we have also the possibility of doing bindings of to already existing C code, C library, so pure C, not Cython. But if I have a library like, I don't know, like Numpy is doing for the linear algebra, the BLAST library for doing linear algebra. So you can also, there's a possibility also to grab these C libraries and provide an interface to use it from Python. Here I mentioned an example in the in the folder that you copied from the location before, and there it's showing how it's done with Cython. So here you see we have so a function to compute the to give me the nth Fibonacci number that I will request. But yeah, so then you have here all the corresponding set, well, the C code and the makefile and the setup.py and the wrapper written in Cython. So as I said, Cython is not just getting a Python code and defining data types. It has a lot of many different functionalities, and it can be used actually for wrapping C code or C++ code. So here you can experiment with this later. You have a minimal example of how would you wrap. We can just run the make, and we hope it will work. Yeah. So you see here you got the compiled Python module that then from my test.py. From my Python module grabs cfif, I import cfif, and then I ask to print the nth the 10th Fibonacci number. But yeah, this is doing under hood by this code, that it's already a binary code already built, and which is coming from a pure C library. So that's the kind of thing that NumPy is doing for all the things that it provides. And then we have also another very mature tool, but for doing the equivalent thing with Fortran. So we have the F2Py tool that you can also pip install, or I don't remember. Yeah, well, it's already part of our Python of the. What I think it must be included here in what we provide with Python, with the Python module, with the Python basic installation.
It's provided with NumPy as well, actually.
Sorry, Olivier, you can feel free to.
It's also provided with NumPy.
Ah, it's provided with NumPy. Okay, it's part of the NumPy package. Yeah, okay. So F2Py it allows me to do compile Fortran code and wrap it and provide me the compiled module that I can, with the interface that I can call from a Python code. So in the, I think, so here there's a minimal kind of hello world showing this. We can see F2Py. Well, here, this is part of the, I think here I won't go through this as we didn't, here is the first, so if you can take a look at it, if you go through the first exercise that I said before, it's as homework or for you to take a look. So it's solving the 2D diffusion equation, but then writing the main part, doing the definite differences in a Fortran function. So the final differences and the evolution of the where I was, so here you can copy paste this and test it. So if you have a minimal routine as this in Fortran, you compile it. You obtain the compiled locally the compiled Python module with the interface that allows you to then from a pure Python code doing just this to execute this function from your Python code, but in the backend is running on the compiled version of this routine. And so here we have some kind of summary. I think some of the things I already mentioned as we were going through them. So as I say, Cython, Cython can deal inside a Cython code with NumPy code. It can do bindings to C code or C++ also, so you can, if you have already there's already present a library that you're interested to using from your Python code, you can wrap it as we saw in the Fibonacci example, so it can provide then bindings from pure Python code to pure C libraries. Then, we saw the examples of the just-in-time compilers. So the PyPy, PyPy is just, it's a main project, so we have to mention it, but we will rarely use it in anything that it's in any kind of code that it's meant to be used for scientific computation. But on the other side, as we saw, Numba is really focused on the community, well, it's coming from the community of data treatment and numerical computation. So it's specialized. It can deal with. You can have NumPy code in the middle. Well, it's a big project and it has a lot of traction. So you can take a look. I didn't look into details at what they are doing with like generating GPU code. So that's interesting to look into. And then, well, Python is just something to experiment with, but yeah, as I mentioned, it's the project is not dead, but moving slowly. Yeah, at some point, except PyPy, that because of not being compliant with almost any kind of the usual extension that we will be using together, except PyPy, all the rest require modifying somehow the code. But the modification by Numba is minimal. Cython really means to rewrite your original function implemented in Python, if it was okay to rewrite it in Cython. And then here I'm just we giving an overview of different options that we have for making use of the different cores that we have on any modern machine. There's in Python, in the Python standard library, the multiprocessing module, so it's available on any Python installation, and it allows to use process-based and thread-based parallel processing, so you can have workloads distributed among different threads or different processes. It can, here there's an interesting link to how it's not trivial if you are doing if you are creating your pool of processes and then you want to distribute the workload between them. It's fine if each of them is working on their own objects instantiated. But if you have common objects, like let's say a big NumPy array that you would like to share among them, and you want the different process to work on different parts of that, it's not trivial how to do that. Here there's an answer from the link goes to an answer from Stack Overflow how to achieve that. But in any case, it's not it's like a hacky way to get a view on a NumPy array. But if you really want to well, if you really want a code to be able to do that, to different with the multiprocessing module is not it's not really trivial how to achieve that. But on the other side, if you're dealing with like embarrassing parallel kind of problems in which the communication will be, you're not going to work on common objects and you need communication only at the end, you can take a look at that. Then there is, on the recent years, there's a lot of development behind this job-lead module, which actually at the beginning it was based on the multiprocessing module, but now it's not the case. It's based on another project. And the thing is, this thing appeared, or the motivation behind it was actually to be thought for scientific usage, so for numerical computations, we can say. And then it's well compatible and optimized for working with the kind of arrays that we have in NumPy arrays, but also like in pandas data frame can be the case also. So it will give me a better interface if I want to do, for instance, if I want to have my different processes working on the same single big array. It gives me a more natural view on those. So so it's something you can take a look at. It's having a lot of active development in the last 2 years. So you will find a growing community of it. But it's mainly mainly still based on, as they mention on their own documentation, all the different methods they provide and the way to communicate between processes. It's still the main focus is kind of embarrassing parallel problems, so you don't have you can work on the same you can have a common view of the memory, but then if for some other reason you need to communicate things among the processes, it's another story. And then we have MPI for Pi, and that's a totally different approach compared to this kind of approaches. If you followed the MPI session, we covered at the end how from Python we can code in MPI using MPI for Pi. MPI is a kind of standard for how to pass messages, as the name it says, how to communicate among different processes. So it's naturally a parallel model in which each process has its own view, its own memory allocated, and you are forced to pass messages among them and to communicate between them. And so it's a standard, on how to achieve that, how to implement that. And then you have different implementations in C, Fortran, C++, and you have the MPI for Pi extension, which is basically a wrapper of the C++ MPI implementation. But if you are already familiar with MPI on C, on Fortran, or C++, you can say that you already know MPI for Pi, because the main thing of MPI is just getting into the logic of this parallel coding via communicating things among different processes all the time. And so MPI for Pi provides bindings to the different revisions of the MPI interface. And the main thing that you get with if you are coding in MPI and you don't get at least trivially with the others is that you can naturally, you are in a logic in which doesn't matter where your cores are going to be distributed, if they are all on a single machine or among different machines. So you can profit of growing up to any number of cores if you have something parallelized with the MPI programming paradigm. So that's also for kind of homework to experiment later on. You can take a look in this same readme that you copied. There was a hands-on first part and hands-on second part. You can go through the second part. The second part actually is the one that it will. In the first part, you were profiling the pure Python code of using the line profiler and kern prof and memory profiler, the 2D diffusion code, which was the one given there is a pure Python implementation. And then in this second part, it will ask to experiment a little bit with like using real-time compilation with Numba, or writing a part of that code with Fortran and integrating it with the, and then writing the solver and evolution part of the PDE in Fortran, and then calling it from the and calling it from a Python, calling that function in charge of the heavy part of the computation from a Python code. So yeah, the second part is a little bit to experiment with these options of compiling just in time or producing a compiled library that you can, with the interface that you can call it from a Python code. You can reach us through the usual channels. You know where to find our emails if you have further questions about this. And here as future references on the topic. So this is clearly a huge topic. Even on Cython itself, you can find full books dedicated to that. And a really nice book, which I use more or less to structure this presentation, is this one, High Performance Python. Now this year there was a second edition that's nice because they got a, so it's a nice book like from 2010, 11, but that was mainly Python 2 based, and it's nice this year they released a second edition, in where they updated things, and especially they made everything Python 3 compliant, and it's a really nice reference, this book, on all these different topics. And here there's a GitHub of some tutorial in which you can experiment with a little bit with these tools. And then also you have, as I said, this is a topic in which you can dig and go and go through, like, very dedicating a lot of time to each of these different parts. So if you click on that link of the Praise training Python in high performance computing. So Praise, I don't know if you're aware of it. It's a partnership or consortium among countries part of the European Union in order to aid or support the HPC development in Europe, and they provide in this platform Future Learn, sponsored by Praise. You will find this massive online course. Actually, it's Python in high performance computing. But here, as you see, you can actually join it for free. You can create your account and join it and go through the course for free. It's one of these massive online courses. But as you see, going through all of it, it's thought as a total of 16 hours. So you will have a lot of videos, introduction, explanation, and also a lot of hands-on, because it's important to experiment with this thing, to really get into that. But as you can see in here, what topics will be covered is a bit, so a first part in which you will see about profiling tools for Python. You will have an introduction to NumPy, and then you will have also an explanation of how to interface, how to create Python bindings to libraries in other programming languages. And then you have a final part of parallel programming. So the last time I checked, all the parallel that they have here is just using MPI for Py. So actually you have an introduction to MPI, and then you have hands-on exercises dedicated to doing MPI for Py. But so you see that, yeah, they are covered all the things that we just went through, but in another format, in a format that you have to interact a lot. And so I think it's a nice, if you want to keep digging into this, it's a nice thing. And the fact that you have it available for free is quite nice. And wait, so no, I lost my last slide, but yeah, in any case, that was all I had to tell you. So now I will check if there are questions in the chat. And as I said, you can always contact us through our emails. This is a topic that requires a lot of experimentation and learning. So take a look at the hands-on I left there, and yeah, you can take a look at the course if you want to go deeper into all of this.